All right, everyone. Welcome to VSA Online. It's 8 p.m. GMT and very comfortable 10 p.m. in Sweden. So I'm very glad to see you all here joining this time. And I'm very happy to introduce Takis Chytas from, formerly University of Wisconsin-Madison, USA, and newly employed by Apple, promoting VSA and graphs there. Well, without any further delay, Takis, please, the floor is yours.
Yeah, thank you very much. Thank you very much for the introduction. Very much for the invitation, first of all. I didn't know about VSA Online before learning it from you, but after that, I saw some of the previous talks and some of the previous invited people that you had there. And actually, it's very, very helpful for someone that either is new to VSA and wants to learn what the latest state-of-the-art results are, the applications of VSA to different fields. So yeah, it's a very great effort from your side, and thank you very much for making me a part of it. So let me share my screen. Okay, so I hope you're seeing my
Yes,
screen. Okay,
everything is on. Yes.
so yeah, this is about a recent work that was published in NeurIPS 2025, which is about essentially VSAs and graphs. And we propose a general purpose, real life, so it's not like just a concept result, a way to encode graphs, we name this faults. So some very, very brief background is that this was part of my journey as a PhD student in Wisconsin, in the University of Wisconsin-Madison. And also Rudra, who's the second author, is employed from Lawrence Livermore National Lab, which actually led to some further collaboration as I was an intern uh, in summer 2024 there. So as I said, this is about graphs. And why graphs? Because graphs are actually everywhere. Many, many real life problems and real life phenomena can be modeled as graphs, from like proteins to road networks, 5G networks, citation networks. There are many, many different applications of the same idea, that of a graph. And naturally, machine learning was very interested in that area and tried to propose different ways to take this graph, which is some very abstract, weird structure, and convert it through some machinery to something that is easily understandable by any machine learning algorithm, basically a high-dimensional vector. Because then we can use an MLP, a random forest, even KNN to make some predictions out of that vector or somehow understand the graphs. And over the years, many, many different works were proposed. Some of the most famous are message passing neural networks, graph convolutional networks, graph attention networks, and many, many more. And our work actually focuses on that specific machinery and different ways to design the machinery, taking into advantage the VSA ideas. And the main observation that led to this work is that graphs represent collections of higher order elements that can be formulated as multivectors. I know this may be too much to parse. Intuitively, what does this mean is like, yes, we can have a graph as we see it on the left side, but we can think of the graph also as a collection of edges. And an edge can be thought of as like a higher order element. It's not a single node, it's two nodes. And if we had like hyper edges also, we may have, three nodes together or four nodes together. But what is a multivector? So if you just Google, multivector, Wikipedia gives this definition and has a lot of weird keywords in it, like K-blades, Clifford number or Maltor, weird stuff. I'm not going to focus that much on the theory side and on this background. One important keyword is that of Clifford. And because multivectors are highly associated with Clifford algebra or geometric algebra. It goes by two names, but it's essentially the same field of mathematics. And for anyone not familiar with that area, I highly suggest this manuscript that you can find on archive. It's a very, very nice introduction to the topic. And by skipping many of the details about what geometric algebra is, we can thought of it as a ring-like structure, which means we have some elements and we can combine them in two ways, with a multiplication symbol and an addition symbol. Not the typical multiplication addition we know about real numbers, but some other multiplication addition. And the good news is that we cannot just talk theoretically about, multi-vectors and combining them with these operations, but there is an actual implementation, that of tensors. So we have tensor products, we can combine tensors together. There's a whole field of tensor operations that you can that have helped actually get actual implementations of these concepts that geometric algebra talks more theoretically, which is great because this means we can instantiate our idea of representing the graph in that operations by using tensor algebra. The bad news is that it's a bit hard to work with that operations, and because as you can see from the diagram, this grows in dimension the more things we combine together. And if we represent each vector initially as of a dimension 1k or 2k or 4k, you can understand that this can grow very big very quickly. And actually for Clifford algebra, if you want to be strict mathematically, if we have an n-dimensional space, we need a 2 to the n dimensional space to represent the whole Clifford algebra as it described by mathematicians. So on the one hand, we have Clifford algebra, an actual implementation, but if we care about being formal, mathematically correct, we need a generic implementation of O to the n. And the key word here is that of generic. Because the truth is we don't need some general Clifford algebra, we need Clifford algebra only for graphs. So maybe we can somehow cut some edges in a formal way, of course, and somehow get to something that is more attractive in practice. I will not get into that much of the details because this will take a lot of hours talking about mathematics. But the first step is that we can use what is called the Dirac operator, which is formally derived from Clifford. So we don't have any discounts there on the mathematical formality. But we go from something very generic to something that is very graph specific. So we reduce our scope to only graphs and maintain the mathematical rigor required. But the thing there is that if we move away from Clifford algebra, suddenly the implementation details become a bit fuzzy. How can we implement that in practice anymore? Which takes us to the next stage, which is basically we can connect the Dirac operator to what is called the spinor space and a Fock space, because we can show that the Dirac operator operates on that spinor space, and then consequently the spinor is realized as a Fock space using this annihilation and I forget the other keyword operators, which is an okay step, but still the implementation is not that attractive. It can be better than the original from Clifford algebra, but still it can grow. The size can grow a lot the more operations we stack together. But the most interesting thing out of this chain of mathematical reductions is that there is a work which is called the Fock space toolbox and some applications of computational cognition, which basically talks about Fock spaces and VSAs. So basically, they design some operations that operate on that Fock space, but they're realized as a vector symbolic architecture, which means we have a complete connection from our original Clifford algebra to this work, which is not some ad hoc choice, but is mathematically motivated, at least for graphs, which is the focus of this work. So we have that work, but as we said, still the operations are not that attractive in practice when we work with high-dimensional vectors. But since we're talking about the VSA, then we can afford some engineering cutting of edges. And instead of using something that is very formal, we use something that is again a VSA, but is way more attractive in practice, something that is called the holographic reduced representation. I guess many of you here are familiar with that word, but basically it says that the vectors here, the original like vectors belong in some space Rn, and the two operations can be realized as element-wise addition and circular convolution, which means that if we multiply using that circular convolution vectors together, the resulting vector is of the same dimensionality, which is great for practical purposes. Of course, this comes with some noise in the result. And the main question now is whether we can afford that approximation, that noise, in order to have something that people can actually use in practice and not just some theoretical result that, it can lie in the mathematical perspective of VSA, but not really help practitioners that are interested in applying VSA ideas in graphs and graph machine learning. So before going into the results, this means that in theory at least, we have a machinery to convert a graph to a vector that is parameter free, that can be fast parallelizable. And also it's quite generic, as we will show, because we didn't make any assumption about how the graph looks like, whether it's like also a hypergraph, maybe, if it's some weird graphical structure. All of our steps were based on the fact that we deal with a graph. And another byproduct, which is like a happy occurrence of that thing, is that since this is parameter free, this means we can use any predictive model to predict the tag or whatever is associated with that graph, in contrast to, for example, graph neural networks, which requires an MLP head. We cannot stack, for example, a random forest on top of a GNN and make this work because we don't have any gradient flow. But in our case, since the first part, the encoding of the graph is parameter free, so we can train free, we can use any model from this rich machine learning literature to get the best possible results. So yeah, in theory, we have something that works great. Now the question is it great? Because we can have something that is very, very fast, very efficient in obtaining graph embeddings, but it can be noise. So basically, we don't have any signal in these vector embeddings. To assess the quality of the embeddings, we try to be as thorough as possible and examine many different graphical structures, many different scenarios. And we started with some very, very simple cases. Some simple graphs like GraphQA or HyperGraphQA or Jaffe, which is about proteins, and questions like, how many nodes are in this graph, how many edges, whether the graph has any circles and stuff like that. So the procedure is we encode everything using our HRR-based algorithm. And then in this case, we're using a very, very small MLP. You can see the model size on the second row to predict the label associated with that question. And as you can see in all cases, although the MLP is very, very small, like 8K or 16K parameters, we obtain results very, very close to ideal, which gives us more confidence that, since the basic knowledge about the graph is still remains after we do the whole encoding procedure, maybe we can extract even more knowledge out of these graph embeddings beyond, whether it has a cycle or how many nodes it has. The second experiment was more like protein-based experiment. This there is called PPI. So basically here you encode the protein and you have multiple labels, not a single label, but you have actually a multi-classification task, if I remember correctly. And actually, our approach, FODS, is first of all an unsupervised method, but is by far the best unsupervised method. And even more interestingly, it's on par with the best supervised methods. Like you see some common suspects here, like GAT, GCN, LGCN. And our approach is like, almost the best one, very, very close to the best one, which is GCN and II. But PPI is thought a bit of like kind of a saturated benchmark. So we tried with even more challenging data sets. And one of that is called more HIV. There is actually a leaderboard available online with very, very highly specialized baselines like hyperfusion, PAS, HIG. These are very, very highly specialized baselines designed specifically for that dataset. And our approach, without any such specialization, is performing equally well. If we use, so we have, as you can see here in that table, we have two entries. The bottom one, which is plain false, means we're just using our simple machinery for encoding a graph without any extra information about the problem. And in that case, we are performing actually slightly better than GCN and GIN, which is like the two most common go-to models for graph encoding. And when we're adding some additional information about the problem, which is like this fingerprint, each molecule has some fingerprint, which we can add because our approach is very generic and we can handle additional information on the node or on the edge side, then we obtain a method that performs actually in the top 5 of all the publicly submitted benchmarks there, baselines there. So in total, we examined actually 22 datasets. I'm going to have all of the results here, but the key observations is that our approach is always one of the best. It's not like highly specialized, it works only for some specific applications and some others it trades by a lot. While at the same time is orders of magnitude faster, it's CPU based, it doesn't require any training, any gradients flow, and it's very sample efficient for the same reason. Because we can use, KNN or AutoML to find the best machine learning model to predict the label out of these vectors. Additionally, since we're talking about VSAs, since we didn't really care that much about in our work because it's about encoding graphs, but actually we get some other properties for free. And one is that, in theory at least, our encoder is lossless. It's more like an autoencoder. So we can encode the graph to a vector and then obtain it back by basically using the inverse operation that is offered to us for free by the VSA. And for HRR specific, we have an approximate inverse and the exact inverse. And the difference is that on the computational aspect, the approximate inverse is way faster than the exact. And we can see that if we have a graph like the one on the left side, and we try to encode it and then reconstruct back the edges, we depict on each edge the cosine similarity. And we can see that as we increase dimensionality, even for the approximate inverse, which is way more noisy, we can see a clear separation between the cosine similarities of the true edges and the cosine similarity of any phantom edges that may try to like reconstruct back. While when we have the exact inverse, the results are like amazing. And even for the result of 16, the separation not only clear, is basically the cosine similarity is practically 0 of the wrong edges. The cosine similarity of any correct edge is very, very close to 1 or even 1, exactly 1. I'm pretty sure you are familiar with these results. This is more of the, this classical result we have seen in many VSA papers, which says if we bundle many binding pairs together, how clear it is whether we can reconstruct, whether we can obtain only the correct pairs and not have any phantom pairs, any fake pairs in our prediction. This is for the dimensionality of 4K in the vectors. And actually, this is with the approximate inverse, not with the exact inverse, just to show that even when we have a huge graph with 300 pairs, and you're using the approximate inverse, which is very, very noisy, the separation is very clear, and you will have only few edges misclassified as like being actually there in the actual graph and not being in the reconstruction, or not being there in the actual graph and being there in the reconstruction. So yeah, that's not something that we examined a lot in our work because we care more about the predictive probabilities of faults, but it's a very nice additional advantage that VSAs can offer over, typical graph neural networks. And since we had a general purpose graph encoder, the next question that we were starting modeling about is whether we can have a graph language model. I'm pretty sure you're all familiar with multimodal language models. For example, like Speechverse on the top left, where it combines text with audio, or any VLM that combines images with audio. The general approach, as we can see on the bottom, is that we have some extra modality, that using some modality encoder that is good enough and strong enough, like clip for images, we can somehow connect it with an LLM so that the LLM can understand that additional modality and reason about it and answer questions about it, basically. And since we have a pretty good modality encoder by itself, like the folds, it appears to be a pretty good graph encoder for many different types of graphs. We thought, why not try to combine that with an LLM and see if we can create an LLM that we can understand proteins and can answer novel questions about proteins, or graphs in general, road networks perhaps, or citation networks. And we did some preliminary investigations. Obviously, we didn't have the resources to create a large-scale foundational graph language model. But what we did was along these lines. So after we obtained the graph vector representation using folds, we used simple linear adapters and prefix tuning, which means the whole LLM was frozen and only the adapters were trainable to create a graph language model. Create a model that, given some question like, does the graph has a cycle, you can say in text again, not by a single prediction head, a binary prediction head, yes, this graph has a cycle, or no, or how many cycles it has, or any other question that we can think about. So before going into the results, since we're having folds, which is train free, and we're using only linear adapters, and the LLM is frozen, this means that the whole architecture is pretty easy to train and very lightweight. And since we're not making any assumptions on the graph structure, on the graph format or whatever, it's quite general in practice. And we tried first to compare ourselves with more specialized graph language models. Graph token is one of them. This is from Google, actually, and they try to combine a graph neural network, a graph convolution neural network, with an LLM. I think it was Gamma back in the day, and ask some basic questions about graph, just to showcase that the LLM can understand the graph encoder, the graph embeddings, and can answer questions in text about it. Like, for example, how many nodes there are, or how many edges, or even more complicated questions that even a human would have some hard time understanding, takes some time, like how many triangles there are. And you can see obviously the drop in the performance since this question is way harder. And the good thing is that our approach is on par or even better than graph token. So it's better than a model that trained a graph neural network for that specific dataset and then had the graph language model to answer these questions. And yeah, Folds LLM is basically way more generic and it can answer the same questions with the same or better accuracy, which gives us some more confidence to try even more ambitious datasets, even harder datasets that actually graph token and some other works that exist, like GraphLLM, couldn't handle at all. For example, Hypergraph QA was a dataset that we created along the lines of GraphQA that GraphToken created, and it proposed the same type of questions, but the graphs were no longer simple graphs, but they were hypergraphs. We had hyper edges that maybe, we had an edge that connected five tokens to five nodes together, or 3, or 10, or whatever. So suddenly we had some graphical structure that no other graph language model could handle, and the only approach that someone could take was by doing zero shot or few shot text-based question answering. So basically, describe the whole hypergraph in text, like for example, edge 1 connects node 5, 10, and 11, edge 2 connects node 5 and 2, and so on and so on. So a big text-based description of the graph, and then ask the question. As many works have shown before us, large language models out of the box are not very good at answering text-based, understanding text-based descriptions of the graph. So you can see that the accuracy, especially for zero shot, is very, very low. Few shot, you have a slight improvement, but this is again far from ideal. In contrast, FODGLLM, since it uses an encoder to encode this hypergraph, it has a clear improvement over these approaches. But beyond hypergraphs, we also tested with proteins, because proteins are like everywhere around us, and there is a huge effort on creating models that can understand proteins without omitting any of their information. So some initial works from DeepMind back in the day, they were actually omitting a lot of the information about the structure of the proteins. They were providing only the sequence of amino acids, but nothing else, like the 3D structure of the protein, which can be a disadvantage in theory. So for Jaffe, which is a protein dataset, we again took the same route. We encoded the proteins with no changes basically in the encoding stage, and we had a graph language model that could understand way better than zero shot or few shot learning and answer questions that people that work in that area in protein-based machine learning care about. And beyond these improvements, like the performance improvements, another aspect is that of speed. When we're doing zero shot or few shot, this means we need a huge text-based description of the graph. And in few shot, this is even worse because we need many graphs in the prompt, which can be quite bad because we know that the complexity of the transformer is based on the square of the number of tokens. So we can see that the inference time is quite high. GraphLLM is again an LLM that combines a GNN with an LLM. It's a graph language model that combines that. So this is way faster, obviously, than these approaches. At the same time, FODGLLM is also at the same scale, but even faster, because our encoding is actually even faster than that of a graph language model, a graph neural network, sorry, because it's CPU based and it's parallelizing. We can encode different parts of the graph at the same time using multiple threads or multiple processes, and then combine them very efficiently and very fast. So yeah, the takeaway is that without any degradation in the performance, we have actually a method that can handle different scenarios, different cases of graphs, hypergraphs, proteins, being on par with more specialized works that combine graph neural networks or graph attention network or whatever with an LLM. So we don't lose any performance there. We can handle more use cases, and the inference time is actually even lower because of the CPU-based approach. So yeah, I don't have much. I'm in 30 minutes, so I'm a bit faster than I expected. You can find the work either on Europe's 1025 or on archive. You can see the link in the bottom. And also the implementation is available to all of you to experiment with and build on top of that. So thank you very much. And if there are any questions, I would be happy to answer them.
Takis, thank you very much for your talk. Very exciting. So now I open the floor for questions. So we have one in the chat. On your lossless slide, do we know why the approximate inverse causes the scores
Yeah.
between nodes to decrease, even though they still appear to scale in some consistent way? Is there a way to boost those scores, and does that actually matter?
So the good thing of using a VSA that exists and not rediscovering the wheel is that you don't have to answer that questions. VSA has already answered that questions for you. So if you read, for example, the HRR paper, they talk about resilience to noise, how many pairs they can combine together because the results become pure noise. So the easiest modification would be to find a VSA that's more efficient without having to crack your head and trying to find something that is better for your side. If you're asking about is there a way to boost those scores, then you're getting a bit more you're kind of overfitting to maybe a specific data set or maybe a specific graph instance. So that poses a danger that maybe you win something but you lose something else. Sure, maybe there is some way, but yeah, I would say the most correct way for me would be to find another VSA that is better if there is such, or else be prepared to pay the computational cost of using the exact inverse in contrast to the approximate inverse. So yeah, I don't know if this is if this answers your question.
Yes. So let's move on. I have a question myself. So I worked with graphs and codings, and I know I feel the reason for why it is good. I mean, for training simpler linear classifiers or something. And indeed, the performance is on par with more complex models. What I struggle to understand, what is the nature of interaction within LLMs when you kind of um, append it as prefix? So this I don't understand actually. So maybe you have thought about it. Can you explain?
Yeah, of course. So that's, I think, a more general question about multimodal language models. Because whether it's an image or audio or a video, at the end of the day, you're giving one or more encodings of that modality to the LLM, and you hope that the LLM understands that. For the graph, in our side, since we know that the graph encoding is strong enough and general enough, that's what gave us the motivation to try that. But why the LLM understands that? That's an answer that obviously I cannot give a very satisfying answer because it's more on the multimodal language models and how does even more parameters, more data, better encoders do the trick. I don't think it's more something specifically to graphs.
No, it's exciting to see all these positive results that you
Yeah.
show, but it really appears as almost as magic that it happens.
Yeah, yeah. It is it is magic. I don't know. It's all about scale, I guess. So our experiment was like with a 7B model.
Mm.
So a relatively large LLM, let's say, at least for academic purposes, not for commercial
Mm.
purposes. But I mean, if you had an LLM that was like half a billion parameters, I don't think we could obtain the same result. Just like we don't have good VLMs with half a billion parameters. So yeah, it's more on the multimodal language models. How does this happen? It's a combination of, I think, more parameters, better data, and better encoders, better modality encoders. And since we had a good modality encoder, this gives us confidence to attempt that.
Okay, fair enough. So let's see if we have questions in the audience. So we have another comment in the chat. I'm not sure how any given LLM can understand the data you injected with prefix to a given disparity between the nature of the vector spaces and the different encoders. Well, yeah, that's pretty much in line.
You're using some adapters. These are the trainable parts of your architecture in any multimodal language model. So you have the encoder, which indeed operates in some space completely unknown to the LLM. But you bridge them together using some translator, let's say, which can be either, a simple linear model or something more advanced like a Q-former that some other works have used. I think Instructively has used a Q-former. But you kind of translate your modality vector space to the vector space of the LLM so that the LLM can somehow understand these vectors, position them, these vectors in its latent space, in the latent space that we can understand.
But maybe, or if you can very briefly summarize the training process. So do you kind of train it in a supervised manner, this adapter, like for a given question, so you know the answers, or
Yeah,
how?
definitely. So I can also share this so we have the reference. Basically, what we're talking about is the bottom half of the image, where we have some modality encoder, and then we have this connector. This connector is the thing that you usually train from scratch, where it translates whatever the modality encoder spits out to the vector space of the LLM. This is not something that we came up with. This is something that, if you use transformers with PEP, this is like the default way to fine-tune a multimodal language model. So yeah, the approach usually, if you cannot afford reinforcement learning, is pure SFT, supervised fine-tuning. So as input, you have your modality, let's say, and let's forget about graph, let's say about images. You have some image plus some question, and then your output is whatever the response should be. For example, if the question is describe this image, the response is this image depicts a car on a street and blah, blah, blah. If it's a graph, it's something similar. If the graph is about, if it's a protein, you can ask what is the second amino acid, and you can say the second amino acid is A, or whatever. And you simply train that using SFT. So basically, you're forcing the connector, because this is only trainable, the only moving part, because the LLM is usually frozen, to align the space so that the LLM produces the response that you want.
No, okay, yeah, I get the idea, of course. Yeah, so it was about fine tuning. Yeah.
And it's the other thing is like there are different levels of fine tuning. The cheapest one is just train the connector and keep the LLM frozen, don't touch it at all. If you have millions of samples, then maybe it makes sense to kind of fine tune also the LLM, because you get more parameters to tune, so you may get a better performance than just fine tuning some small connector. But since we didn't have that computational capabilities, We just train the connector by keeping the LLM completely frozen. The modality encoder is very simple in our case, it doesn't require any training. So yeah, it was a very simple training procedure, very lightweight.
Okay. But did you study the properties after the connector? I mean, so what? I mean, compare it to the original vectors.
That's a good question. Actually, no. That's a honest one. I don't know. Yeah, actually, it's a very nice question. I don't know why I didn't do that. That would be very interesting because basically, in theory, the transformation should be lossless in some way because it cannot collapse all the graphs in one area or something. So it should maintain the generality of the original modality encoder. But yeah, I didn't really experiment with that. No, I didn't do that.
Okay. So let's move on. So, do you have any more questions to Takis? Phil, Tony.
Yeah. Hey, Takis, could you give us a bit more explanation of how you're using, of exactly how you're encoding these graphs? Maybe flip back to that slide that I think has just an example graph because I'm trying to look at the paper on archive
Right.
as well. So you had a slide which had like a little example graph with like 6 or 8 nodes or something.
I guess you're talking about this one.
You are not sharing.
Really?
I don't see that you share.
Oh.
Yeah, we just see a black screen with
Oh.
a message. You are sharing your entire screen, but it's black.
What about now?
Yeah, now.
Yes. Yeah. Perfect. Yeah. So I mean, tell me if I'm understanding correctly. It looks like you have a vector that represents each node, and then you're using the binding operation to represent edges. It's just 2 nodes bound together, and you're constructing the sum of that. That's basically it. And then there's one other feature in there for the size of the graph, I think. Is that right?
Yeah. So I omit the
Okay.
size here, so it would be just confusing because it's more like on the engineering side rather than the formality. But yeah, that's the
Yeah.
general idea.
Yeah. Okay.
If you have a very simple graph with no additional information on the nodes, I have just some random nodes here, 1, 2, 3, 4. They don't have some additional meaning. Because if it was, for example,
Yeah.
protein, you would have some extra information on the nodes.
Yeah.
So if it's something so basic, you're doing just like that, what you described.
Yeah. That's a super basic representation. And then when you're doing things like these tasks for like number of nodes, number of edges, cycle existence, etc. What was the okay? So there, yeah, I'm seeing I'm looking at your archive paper. Yeah, there's a column for the performance of FOGE LLM, and so that's when you were injecting these as embeddings into an LLM. Is that correct?
Yeah, that's right.
Yeah, and you had it trained on that LLM.
Exactly.
Yeah. And then so there were like performance. So it did very well on detecting the number of nodes. It did very well on cycle existence, and it did okay on number of edges. And yeah, that one on the bottom right on So bottom left is the one I was looking at, in the paper. Yeah. And I was wondering cycle existence. So if you're just putting this this embedding into an LLM, I'm surprised it does so well. What size graphs was it working with? Were you working with here?
Right. The graphs here because we want to show comparisons with graph token, we used what they used for the benchmarks because we didn't have access to their code.
Okay, okay. And were those graphs just like a handful of nodes or dozens of nodes or hundreds of nodes?
It was definitely less than 100. I think it was around the range of 20 to 50. So not terribly small,
Okay. Yeah.
not huge.
Right. Okay. Yeah. So cycle existence in a graph of that size is not a trivial problem. You need to do it accurately. You need to keep track of things accurately.
Yes.
Okay.
Yeah, that's right.
Yeah. 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 And then number, right. Yeah. So do you think where it didn't, I mean, these are not difficult tasks if you're just writing a conventional computer
Sure, sure.
program. What do you think the reasons were that it didn't get perfect scores? Was that noise, or was it sort of that it was using heuristics to do it, and those heuristics only work some of the time, or what?
So actually, there are two layers in that question. So the thing here is that we're combining code with an LLM. So we can never be sure that whether it's like our encoder or the combination of our encoder with the LLM. So maybe we didn't have enough samples to fine tune what I talked before about like the connector part. So what I would suggest is like if you're interested about like number of edges, for example, specifically, you can look at that question on folds on its own without the LLM part. For example, here, as you can see for GraphQA, which is like the same dataset, when we're trying to extract the number of edges, we're getting a mean square error of 0.03 without an LLM. This is we encoded everything using our machinery, and then using these graph embeddings, we trained an MLP to predict the label. So we don't have this additional LLM that maybe we didn't do a very good performance on fine-tuning it, or we didn't have enough samples to fine-tuning it properly, or something else happened. So
Yeah.
that isolates better what you're asking. Is that right?
Takis, sorry, Tony, may I intrude your
Yeah,
discussion?
yeah, absolutely.
Because I had a question, a similar question, and the question is whether you tried to train, other classifiers just on the labels. I mean, without LLM, and what was the performance then?
Yeah, these are these results. These results on that side are without any LLM. These are just classifiers or regressors on top of the graph embeddings before going to the LLM.
Uh-huh. Which one? So the top one, or
All of them. All of them here, they come before the LLM part. So everything you see here, all of these datasets, were just folds plus some predictive head, not an
okay,
LLM.
okay,
Yeah.
okay.
And what are you using to make the predictions? A feed-forward network or some other?
Yeah, so for the top image, the model size is basically an MLP, what I'm saying here. And you can see like the parameters are like just a handful. So it's a very small
Yeah.
MLP. Here, for the other datasets, basically for the right one, for PPI, if I remember correctly, we used gradient boosting or random forest, one of these algorithms. I don't remember exactly. And for that, because it was more, the dataset was way more challenging, we just used AutoML with a time limit of 5 minutes, and we just let AutoML to find the ideal ensemble to predict the label out of these embeddings. But yeah, you can use whatever ML model you like because it's train free. So you're not tied somehow. You need gradient flow to train the whole thing end to end.
Yeah, yeah, of course.
Yeah. Yeah. And the representation you're using doesn't really do any abstraction at all, does it? So I'm thinking of like an abstraction might be if, say, you had triangles in your, a large number of nodes and a large number of disjoint triangle subgraphs, that an abstraction would pull that out to sort of represent those triangles in a, in a way, but there's nothing here in your representation that would make the triangles a salient feature. It has to be, a triangle among nodes A, B, and C is like completely different to a triangle among nodes D, E, and F. There's nothing that makes those similar in this representation you're using, correct?
No, I get what you're saying. So, okay, what I can say is that out of all the experiments, what we observe is that the representation we're getting is very truthful to the original graph. So, as we saw also from the decoding thing, it keeps a lot of the information of the original graph in it. So you can think of it, let's ignore all the engineering noise, you think of it like a one-to-one translation. So the vector we obtain from the graph, it has all the information that the graph has, but in a different format. Let's assume that the vector dimensionality is huge, so we don't have any noise. Then the question is how well can be extracted that specific piece of information, like the number of triangles, from the prediction head. If you use, a linear regressor, maybe it's not sufficiently good. For the small tasks, a small MLP did the trick because maybe it was very clearly separated in the latent space. But for more advanced tasks like proteins or this like more HIV, we needed something more advanced to extract only the information we needed. Whether that was like some more in-depth structure of the proteins or the number of triangles as you asked. So yeah, I think it's more of a question, assuming that the representation is very truthful to the original graph, how well we can extract that specific label from the representation. So yeah, if no graph neural network can do that, maybe it's too much to ask. It's too much to ask also from our approach. If all the GNNs have like 5% accuracy on a specific task, maybe it's very hard to expect from our approach to have like 95%. But I can compare ourselves to an ideal graph neural network, let's say. If a graph neural network can squeeze all the protein information to a vector, we can also do that. That's the bottom line, I think. We cannot ask for miracles. We cannot ask for like, a model to predict with 100% accuracy, something that is very hard for any model to do. But if a model can do it with a specific accuracy, probably we can do it with the same accuracy or even a bit better because it's more truthful representation.
Okay, thanks.
But I think this question is still, at least to me, is a bigger one to understand what's going on with the encodings, because I mean the encoding you use is one of many you can do, and even within this our community, people suggested several of them, including GNN inspired, like walking, including walks on the graphs, so where you can actually some graph features emerge by the virtue of encoding. But yeah, so still
Yeah,
it's. But it's
if I can
still
add,
it's quite interesting that it kind of I mean your classifiers somehow fetch this or
So
Feature. I don't think they are features, but somehow they're able to classify it.
yeah, let me put it in a different way. We know that we can decode the vector back to the graph with high accuracy using like the inverse operation of the VSA. We know we can do that. Now, if we can,
For some sizes of the graph.
yeah, of course, of course, of course. Then noise comes, but yeah.
Yeah.
If we can do that, then let's say we write a conventional algorithm, a Python algorithm, to extract a number of triangles and give us the answer. So we have like a two-stage process. We're going from a vector to the graph by decoding it using the inverse operation. And then we're using some specialized algorithm to get the triangles.
Mm.
If these two parts can be modeled and approximated by machine learning model, then we're good.
Yeah.
Now, how big the machine learning model is, that depends on the question that you want to ask.
Mm.
But if you can make the leap of faith that the machine learning model can learn this two-stage pipeline that you can write customly by decoding the graph and then writing a custom algorithm, then it's all a matter of like training properly the machine learning model to do that.
Mm. Just for your reference, the talk before yours, 2 weeks ago, it also dealt with the graph encoding. So if you're interested, you can have a look at it.
Okay, definitely.
Okay, so let's see. Do you have more questions, Tony? So are you happy? You have?
I'm good. Yep.
Yeah, I hope I answered that at least to some
No,
extent.
yeah. I mean, it's open discussion. So let's see if we have more questions.
But in general, surprising or not, they work well. And I know that also like from other collaborators, I cannot say much, but I know that also for real life data sets that they care about, it works well. And it's always on par with heavier, more specialized models. It's never like, a huge jump down, like a huge decrease in the performance for a specific data set.
Mm-hmm.
Why? Yeah, that's an open question. Maybe more mathematicians can answer that more formally than what I do.
Mm.
But I know that we never saw, for that specific instance, all the other methods are getting 80% and we're getting 30% or something like that. We never saw that in either this paper or in any follow-up work that we know that has happened. But yeah, I mean, it's not like we're proving something mathematically, formally, that this is true or something.
Okay.
Okay.
Maybe some people from the audience are more interested in proving or disproving what I'm saying.
So I have one more question. So I'm looking at, so you give these graph encodings to an LLM in your FOGE-LLM system, and you're training it on some data set, I presume. Is that correct? Yeah. And then when you give it new examples from the test set, what are the node representations there? Are those node representations shared with the training data set, or are they just random vectors again?
It has to be the same, right? So the modality encoder is fixed, and obviously you need to use the same recipe. You cannot use like a different modality encoder during training and a different modality encoder during test. So all the hyperparameters of the encoder has to be fixed. Just like it's the true for if you're using an image encoder or an audio encoder. You cannot change.
Yeah, no, I get that the hyperparameters are the same, but suppose you just had, a really small training set with 5 different nodes and you had a number of graphs on those nodes, and now could your test set have a new node that has a different vector representing it, or it's
probably not. Probably not.
Yeah. So I'm just asking what you used to get the results you got.
Yeah. So yes, in general, your train set should handle everything that size-wise exists in the test set. You cannot introduce
Yeah.
larger graphs during the test phase.
Okay.
This is
Yeah.
if you have chosen the node representations kind of randomly, because there are many other ways to represent the nodes. For example, in some experiments, in proteins, you have a clear sequence. So the nodes are not random, they're kind of numbered 1, 2, 3, 4, 5, and there is like a sequence there. So instead of having random representations for the nodes, you can have, for example, the sine cosine embeddings that transformers using back in the day. If that's the case, maybe your LLM can then extrapolate to more nodes.
Yeah.
So if you have some recipe to generate the node representation that is not just random, maybe then you can extrapolate to larger sizes. But if it's just some arbitrary rule that you came up with, I don't think that can
Yeah.
happen.
Okay. Yep. Okay. Makes sense. Thanks.
Yeah, makes sense. Yes. So now I see we are approaching the end of the hour. So maybe I can check if there is a last question.
Yeah, there's another question from Madeline.
So we have a question from Madeline. So can you maybe summarize? May I ask you
Right.
to work as a GPT?
Yeah.
Please
So,
summarize the question.
so what is the difference between unsupervised pipeline and supervised pipeline, basically? That's the main question. And why ours is unsupervised? Ours is unsupervised because during encoding the graph, nothing data specific is happening. If you use GNN to encode the graph, you need to train the encoder to work on your specific dataset. That's a supervised approach. Unsupervised in the sense that the representations are unsupervised. Obviously, then you need some training to extract the label out of the embedding. But the unsupervised versus supervised is more on how you obtain the embeddings. If anything, task specific or basically data specific is happening during the encoding phase. So we didn't do this separation. We didn't came up with that like distinction. Existing works have that distinction. So we just followed along with that distinction. So yeah, I hope this answers your question.
All right. So let's see. Let's poll for another last question. So do we have any? 1, 2, 3. Sold. Takis, thank you very much for
Thank you very much for the opportunity. Thanks.
yeah, and
Thanks.
I hope to see more exciting work from you and spread the word in Apple about us. So we have plenty of other ideas. So, and thank you all for joining this time. And next time VSA Online will be active is in 2 weeks. And we will have, so April 13th, so we'll have Marco Bronzini from University of Trento, Italy, speaking about hyperdimensional probe, another exciting journey into VSA and LLM. So stay tuned and thank you for today. Bye bye.
Thank you very much.